Okay, welcome back to another video. We're going to take on a difficult topic for some people, which is implicit differentiation. So what is implicit differentiation and when do you use it? Let's talk about the different situations and get going on that. Okay, so no explicit dependent variable. What does that mean? It means that the y is not by itself. So if you have y with a function of x, that y is not isolated. So typically with implicit differentiation, you'll see this notation, dy dx. This is called Leibniz notation, and it's commonly used when you're connecting one variable to another. They don't always have to be y and x. Often in calculus, you'll use x instead of time as well, or time instead of x, I should say. In any case, the key to it is when you encounter a y, you need to use the chain rule. So whenever there's a y, you need to put a dy dx after you take its derivative. Let's take a look at our first example here. Here we have an equation of a circle, x squared plus y squared is 100. And we're going to just go through the equation term by term. We don't need to isolate for y and just take those derivatives. So the first term is x squared, its derivative is 2x. And then the second term, its derivative is 2y. But y depends on x. So that's why you're going to put a chain rule there of dy dx. And that's the key. Follow that pattern. Whenever there's a derivative with respect to y, you're going to do that and then put dy dx after. Finally, the derivative of 100 is 0 since 100 is constant. Now it's a matter of cleaning things up. Let's isolate for dy dx, and that is your final answer. So let's move that 2x over. It becomes negative 2x. And then to get rid of the 2y, we're going to divide both sides by 2y. And there you go. That's the final answer. I'd like to try 3 more examples, and believe me, if you can do these examples, you are going to be just fine with this topic. Some of them do get a bit more involved, and hopefully you can be comfortable with it. I typed this one out because I didn't want to do it by hand. I wanted to make it look nice and pretty so you can follow along. Notice this example here, of course, does reduce, and I should just take that extra line of writing there before we move on. So let's move on now to another example. Okay, I don't care what the graph of this looks like. If you sat me down for a few minutes, I could do some stuff and figure it out. Furthermore, you could isolate for y, but the problem is you're going to have a plus or minus square root. Anyway, let's keep it as it is and take its derivative. In this situation, we have a product rule. So there's the template for the product rule. Recall that for the product rule, we take the derivative of the first part, which is x, and that's 1. And then you leave the y squared alone. Then you're going to leave the x alone and take the derivative of y squared. The derivative of y squared is 2y, but remember, you got to put a dy dx after. That's that chain rule. The 3, its derivative is 0, no problem there. And now you just have a bunch of terms, one of which contains a dy dx. Let's get that isolated. I'll just smooth it out a bit by getting rid of all the brackets. Similar to the previous example, we're going to move a term over and then divide by something. So let's move the y squared over and then divide both sides by 2xy. So there you go. This reduces. As you can see, there's a y in the top and the bottom. So just do that extra step there, and you're good to go. Let's try another example, see how that goes. Let me know in the chat where you're from. I'm curious, I'm getting a lot of emails and messages from lovely people all over the place. Let me know where you're from. What's the country? What's the city? Whatever. I want to have some fun times talking to you in the chat. You guys are lovely. Let's keep on going. Here we go. So, this one sucks. We have a bunch of terms here, but that first one is a product rule. The second term and the third term, the x to the 3 and the y to the 4, they're a little bit easier to deal with. But let's get rid of that product rule off the bat. So I didn't show the little steps here this time, but if you follow the previous example, I applied the product rule there. And notice that with the derivative of y cubed, we have 3y squared and the chain effect, which is dy dx. Now on to the remaining terms, which are a bit simpler. The derivative of x to the 3 is 3x squared, and the derivative of y to the 4 is 4y cubed with a chain rule of dy dx. Of course, the derivative of 5, which is a constant, is 0. Now, there are several terms here, but 2 of them contain a dy dx. So let's just clean up all those brackets and organize a bit. This is potentially the more difficult question that you would encounter because there's lots of terms and perhaps you're getting scared of the algebra. My opinion would be to put the dy dx is on one side. Any term that has dy dx stays on the left, and any term that does not contain dy dx goes on the right. So there's the terms that have dy dx. Let's keep them alone. Do not move them anywhere. And the ones that I moved over, you saw, were the negative ones in yellow. Now, the pink is going to be factored. You see that dy dx appears two terms. Let's take out the dy dx from those two terms by factoring out the remaining part. And there you go. Now we have a quantity in brackets multiplying the dy dx. Although it looks scary and lengthy, let's just take that item there in purple and divide both sides by it. I don't care the name of it. I'm not going to read out the letters and the powers, everything. Just take the thing in purple and move it to the bottom of the other side. Think of it like a picture. There. I just moved it down to the other side at the bottom. And now we have this ridiculous looking fraction, but that's the answer. These questions, you notice that dy dx contains x and y in its derivative. Typically with implicit differentiation, the derivative will depend on both x and y. And this is because the original equation is a relation, not necessarily a function. That means that for a given x, there are possibly more than one y. So if you want to find the slope somewhere, you need to know the slope at the x and y value to be specific. Last example. Okay, so this question involves a chain rule in the left side involving a bracketed quantity to a power. So we call this the power of a function rule in an earlier video, or perhaps just chain rule for other people. They may have just called it chain rule. So let's apply that technique to the left-hand side. So you see I brought the 7 to the front and then made the power to the 6, but we still have to do the chain rule on the inside. So we need to do the derivative of 2x plus y. This becomes 2 for the derivative of 2x, and the derivative of y is 1 dy dx. You always put that dy dx. Or in other words, the derivative of y is literally dy dx. Now the right-hand side, yikes. Product rule. Don't get mad. Sorry. Better here now than on a test. This is what I tell my students all the time. Better with me in person or on this computer thingy than on a test. This way, there's no surprises. Anyway. Okay, let's do that derivative. So, oops, that's a lot of fun. Anyway, we have the product rule. So you see the derivative of x is 1. Then you hold the y cubed. And then you hold the x. You don't touch the x. And finally, the derivative of y cubed is 3y squared with the chain rule there, dy dx. There are two terms that have dy dx in them once you expand this all out. So this is going to be a little bit annoying, but that's why, again, I typed this one out because by hand, this is not fun. I sympathize with you because as a student, I had to go through that too. But in the future, showing to someone else, perhaps the typed version is a little bit nicer. Let me know what you think of this approach. So you see here, I'm distributing into the brackets, the 7 bracket 2x plus y to the 6. Multiplying that by 2, you get a 14. 2x plus y all to the 6. And then you're going to have the pink item on the outside multiplied by dy dx. So you literally just stick them together. On the right-hand side, let's just smooth out those brackets. So there's y cubed. And finally, we'll have our 3xy squared dy dx. Now, let's get the dy dx's on one side. And any other term that does not have a dy dx will go on to the right-hand side. So move these guys to the left and move the rest of the stuff in yellow to the right. So a little bit of flip-flopping from one side to the other. On the left-hand side, let's factor out the dy dx. I put a square bracket here because there's already a round bracket. We need that extra level of parentheses here. And now, even though it looks ugly and scary, that square bracket, just take whatever the heck's in there and move it to the bottom of the other side. Don't sit there looking at letters and numbers. Just take that picture and move it to the bottom of the other side. And that's it. There is implicit differentiation. I'm pretty sure if you could do these questions, you're going to destroy any questions you get on a test. Let me know what you think. Hopefully you like this video and you subscribe, and I'll put some more of these nasty questions to make you champs. Talk to you soon.